My name is Jim McCall. I'm a staff chemist with the department formerly known as Fish and Game. I'm in OSPR. I don't know how many of you are familiar with the labs we have in Rancho, Cordova, but I'm out there in Rancho, Cordova at the hatchery building. I'm at the Water Pollution Control Lab. I don't know how many of you know Dave Crane or Pete Odie or Jana Herron. Those are the folks that I'm working with. Sir? I'm replacing Bob Todd. He's been gone a while now. He was the petroleum chemist out there for a while. I have taken over that job. Today I'm going to give you just a balloon tour of what the OSPR labs can do. I'm going to go through that very quickly. We could spend a long time on that, and I could put you all to sleep pretty easily. And then I'm going to talk to you a little bit about fingerprinting. And it's going to be the quickest, least chemistry involved talk on fingerprinting you've probably ever had, and you're welcome. If you would like, if you want to go to sleep later, you can come out to the lab and I can cure your insomnia. So, brief overview of the 5 parts of the OSPR labs. And those of you in the back, if I miss anything, please feel free to. Things have been changing, so we're trying to keep up with that. And if I can remember how this guy worked here. Right and left advances, yes?
Yes.
The other right.
The other right. Maybe I've turned it off somehow. Yeah, I was in trouble before I got here. Chances are good I'll be in trouble when I leave.
Let me grab new batteries, but in the meantime, you can just do the
I can do that. No problem. All right, so here's a picture one of our chemists out there drew for us a while back. Well, not only does that not work, but the keyboard doesn't work. This is another thing I'm pretty good at. Not only do I lose hair, I can destroy electronic equipment as well. Yeah, the whole thing's kind of locked up. It's all right. We'll move on. So the first part of the OSPR Lab Services, the flagship, is the Petroleum Chemistry Lab. It's located in Rancho, Cordova. And what the Petroleum Chemistry Lab is doing is providing tools for you folks who are going out and responding to these oil spills. Primarily what the PCL is there to do is when things start washing up on shore, people get concerned. Once they get concerned, they want to know whether or not this is a seep that was happening naturally or if this is actually a spill that's occurring. So those samples will get collected, taken to the Petroleum Chemistry Lab, and those folks work on about a 24-hour turnaround, give or take, and they can let you know whether or not this particular oiled beach is a result of a seep or if it's the result of some tanker that's run aground. See, look at that. I totally screwed it up. And I told you I was going to get you out early. I'm sorry about that. They can also give you some quantitation, so how much got spilled, roughly, give or take, and they can characterize the product that might have been spilled. Is it diesel? Is it crude oil? Is it this, that, or the other thing? And thank you, Sarah, for doing that. There it is. Here are the things, thank you, Sarah. So here are the things that they would be doing for us. They're going to tell us whether or not it's a seep. They're going to tell us how much might or might not be there. And they're going to provide some other characteristics of the oil so that people in the ICS can make some decisions about it. Technical assistance as well. That's the one thing I want you to take away from what I'm telling you about the oil or the lab services that we can provide is we're there also as technical advisors. We do that for the wardens, and we do that for the folks out on the marine spills. The Water Pollution Control Laboratory is the largest facility. It is located in Rancho, Cordova as well. It's across the street from the PCL. Has a number of different divisions in it. Inland Petroleum and Hazardous Materials Chemistry, that's me. I'm the only one in that right now. We also have an inorganic chemistry section, a pesticide chemistry section, bioaccumulation, and contracts. So what does each one of those do? Inland Petroleum, that's just what it says. I'm there to support the wardens doing inland pollution spills that are happening in the area. Anything that's petroleum related that happens in non-salt water would come to me. My job would be to try and tell them how much was there, characterize it, tell them whether or not that drum leaked into this creek and killed that fish. That's primarily what's happening in that laboratory. Inorganic chemistry, they're dealing with things like fertilizer spills and hatchery monitoring. anything that wasn't organic in nature. Pesticide chemistry is what it says. They're looking in the ag areas for, we have some dead fish that might have come from a sack of pesticide that some farmer inadvertently dumped into a creek, or maybe advertently dumped into the creek. And bioaccumulation and contracts, closely related. These things I've been telling you about, those are immediate impacts. Those are things that are happening right now. Things are dying. The other thing we do that we're set up to do at the Water Pollution Control Lab is look at bioaccumulation in watersheds. Things like mussels, state mussel watch is something we've been involved in, swamp. That's taking a look at the end result of what a watershed does to a specific area. So we're looking at mussels. We're trying to take the pollutants out of those and characterize those and give that back to other state agencies. Water control boards, swamp, SFEI, that kind of thing. And we're doing that primarily through San Jose State University Research Foundation. Inland petroleum, some of the other stuff that these labs will all provide. This is just some of the things that I provide to enforcement personnel. We provide pollution action kits. We put together little chemical snapshot boxes that we send out with the wardens. We train them how to use them. When they're out on a site, they're able to use those kits to collect samples. We also provide supplies for people that are out sampling. Those people might be you. If you're out on SCAT teams or out on first response teams, that kind of thing, we are a resource for you to get sampling equipment. Trained expert witness, haven't had to do it yet, been deposed once. Do spend a little bit of time working with the legal staff trying to be good at that. That's a nerve-wracking thing. I'm sure some of you have done it here already. We also go out when we're called. I tell the wardens I'm 24 hours away, and I will come with ice and ice chests, and I will even come with stuff in the ice chests, if you tell me what you like. And I will transport the samples. So I'm a Sherpa. You know, it's pretty hard to collect that stuff. You go out, you show up with a backpack, you help them collect that stuff, and you bring it in. We also do a little bit of hazardous material shipping. That's gotten much more difficult lately. A lot of regulation about that. And I also help the industrial hygienists with HAZWOPER training so you folks can go out into the field. We also do non-chemical sampling. The department's been interested in sediment cases. There's been a tremendous rise in sediment cases. So here you can see a stream that's been partially obstructed with a lot of sediment from upstream. The third lab, Aquatic Bioassessment Laboratory, that's been on the rise here. I don't know how many people here are familiar with aquatic bioassessment, but the general idea is they go out to an area, they're doing it for monitoring, they're also doing it for enforcement. They randomly pick a spot on a river, and they take a 1-foot section, they scrub that rock, and they scrub all that sediment, and they capture it in a net. That net is then collected into a jar, the jar is preserved, and the jar is transported to the lab, where an entomologist will look at it through a microscope and count the number of bugs and the different types of bugs in that sample, in a subset of that whole sample. Here they are identifying, this is this kind of bug, and they can identify it based on these characteristics. They will take those numbers and they will put them into a histogram, and they'll say, okay, here was the spot that was affected, and here's the spot that was 20 meters upstream. There were 33 different types of organisms upstream 20 meters. Where we had our problem, only 8 of those were able to survive. We were only to count 8 of them. And as we get further and further away from the impact site, we see that the diversity goes back up. It's a really neat and nifty way to monitor a watershed and find things. I don't know how specific it is. I don't know if you can tell, well, this was a pesticide that affected that area. But you can see very clearly that we can get a lot of information out of it. We have 2 others. I'll discuss them very, very briefly. The Marine Pollution Studies Laboratory in Moss Landing. Anybody familiar with them? Just to get an idea? Okay. They are in collaboration with UC Santa Cruz, I believe, and they're doing long-term monitoring in RDA. They are great at sampling. As a matter of fact, I think most of our swamp sampling comes out of that area. And the Fish and Game folks that are out there are running trace metal analysis by ICP-MS. They're also looking at low-level mercury. So they're doing monitoring stuff, and they're working with Yes, sir.
ICP, pardon me.
ICP-MS?
Is that your instant command post?
Yes.
No, this is probably an oversight on my part. There should be a slash and an MS there, not the command post.
I think it's a definition of the acronym.
Yes.
What is that?
I'm parking. I don't know what that
Oh,
is.
I'm sorry. I'm trying to dodge the question. ICP-MS,
I don't
I'm
need
not
an answer.
exactly
I want to
certain
talk about
what those stand for. It's an ion chromatograph and a mass
Didn't know for
spectrometer.
me.
Don't know what the P is. Might be by plasma. Low-level mercury by atomic fluorescence. Some more Greek. Luckily, I'm half Greek, so I could explain some of that. The last one I will tell you about is the Granite Canyon Lab. Anybody familiar with them? That's a really neat facility. If you ever had a chance to go there, it's pretty cool. There's a great big long staircase that'll take you right down to just above the surf. I haven't been there myself, but I've talked to Brendan Phillips, who's one of the fellows that works there. It's spectacular. I'm sure if you gave them a call and you were in the way, they would show you around. They're working with UC Davis. And they're doing toxicological research. So they're looking at monitoring watersheds and estuaries around the California coast. The last thing that I can recall doing with them was dispersant and oil concentration in the water column with dispersant added versus no dispersant added on salmon. So it's pretty interesting. So, I'm sorry?
Where's that lab?
Granite Canyon, I believe it's just south of Moss Landing. Yeah, it's just south of Moss Landing. So that is a very, very basic overview of the 5 labs that are available to help with this, that provide tools for environmental response when there's spilled oil. All right, so when there's a problem, how do we know that this oil belongs to that responsible party? This is going to be 10,000-foot aerial of that process. I'm going to try not to get into any details. Please stop me if you have any questions. I'd be happy to talk about it. I'm going to roll through it fairly quickly, and I may not get to the end of it in the time I've been given. So if you have any clarification or any questions, just please ask. Somebody talked to you already about what petroleum is. Is that true? I won't have to cover any of that. So that's good news. But I will tell you that whatever that person told you today, there are thousands to tens of thousands of individual specific compounds in oil. I know when I was growing up, I just thought, oh, oil, like, oh, sugar, it's all the same. But that's not true. There's a great deal of different compounds in that mixture. It's a very, very complex mixture. Don't be confused by any of the Greek there. Remember, I'm half Greek. I can explain it. One of the compounds you might find, one of those specific compounds you might find in oil is a hopane. Why am I showing you this picture of hopane with all this Greek on it? I just want to give you an idea of what it is we're talking about when we go in to look at specific compounds that we use to do this fingerprinting process. The C30 here refers to the fact that there are 30 carbons in there. This is a 2-dimensional drawing of a 3-dimensional structure. And each one of these little arrow points is trying to indicate that, well, at this particular carbon, it could have gone alpha or it could have gone beta. It's right-handed or left-handed. Depending on which way they go, it's a completely different compound. And for those of us trying to figure out who this oil belongs to, that's a great thing. Because it turns out that all this garbage in this oil, it all gets there based on what went and got buried back in the day. We live at the bottom of a sea of more or less oxygen. And so all around us, all the time, there's combustion going on. You can think of oil as carbon that escaped that cycle. It got buried and is in an anoxic environment, and it is not being combusted. When it's not being combusted, it breaks down very, very slowly, thousands, tens of thousands of years, and it tends to maintain its original shape. So this particular shape here came from this. This is a bacterium. Here's a blow-up of the cell wall of that bacterium, and here's a hopane polyol that happened to be inside of that membrane that may have provided that membrane some elasticity and some strength. You can tell that the difference between those two is this big tail out here with all of this alcohol on it. When that thing got buried, fell out of a water column, got buried, spent a lot of time underground, pressure and heat, very, very slow combustion without oxygen. This got removed, and it turned this part of this bacterium into this compound. Remember, there's tens of thousands of those compounds in oil. And depending on where it got deposited and the conditions in that depositional field will depend how much of each type of that thing is in there. What we're doing as chemists is we're comparing the ratios of those things. And then we're making some opinions about whether we think they're the same or not. What is it that you get when you get a report that says it's a match? You're getting an opinion. You're getting an expert opinion, which, don't tell anybody, turns out it's mine. It always makes my mom proud when I say that. You're getting an expert opinion. You may get a differing opinion. When there's a great deal of money at stake, often you will get a differing opinion. But it's a qualitative assessment of a number of ratios. And you're getting somebody that has some experience with that saying, yes, I believe that these are the same. So responsible parties always want to say no, and we're here to say yes or no. Where does all of this magic hand-waving come from? This is my predecessor, Bob Todd. I'm sorry?
Yeah, same haircut.
Yes, we same club. His all went down to his face, mine all slid down my back. This is a lot of the literature that we have used for the method that the PCL and the WPCL use to fingerprint oil. This is a lot of the literature that's gone into that. It's been a developing thing over the years. Who generates this? It's the people that are exploring for petroleum. We have a very different problem than those folks do. The folks that run this here, well, they're refining, but the folks that are actually out looking for the oil, they have a very, very different problem than I do. This gentleman is going to bring me a jar with oil in it, and he's going to bring me another jar with some water in it that has some oil in it, and he wants to know if they're the same. That's pretty straightforward. It either is or it isn't. When you start trying to explore and drill a $5 million hole, you've got to look somebody in the eye across the desk and say, yeah, we need to drill here, and here's why. They're the ones that are writing all of this. The exploratory folks are the ones that are looking for some comfort when they tell them, yeah, put your $5 million hole over there. It's a good place for it. We're answering a different question than they are, but there's a great deal of literature out there that what we're doing is based on. Fingerprinting itself, you guys are all familiar with CSI and all that. Each fingerprint has different patterns on it. Well, oil has different patterns in it. And those patterns are those compounds I showed you in the beginning, the ratios between them. So take your finger, put it on a surface, criminologist comes in, wipes it, reads those tea leaves. That's what we're doing, and I'm going to try and explain how we can do that using the tools we have available. Our warden goes out, finds a sample, brings it to us, comes into the lab in a jar. We extract that with some kind of a solvent because we want the targets out of the matrix, the tissue or the sediment or the bird. Once we get it out of the matrix, we've got solvent plus product. Goes through a couple of steps to clean it up a little bit. Take some of the solvent off by evaporation. Pass it through some kind of a column with some funky white stuff in it. Get it out the bottom, and hopefully it doesn't mess your instrument up. And put it in these little auto-sampler jars, and that goes on the instrument itself. What is the instrument? And this is the part where I dare you not to fall asleep. I almost feel like a snake oil salesman when I start this. This is a schematic of a gas chromatograph-mass spectrometer, which is a lot of syllables. That's just a fancy way to say separate things apart and then draw me a picture of what those things are. The gas chromatograph itself is comprised of a tube that is between 30 and 60 meters long, and it is hollow, and the inside of that tube is 0.25 micrometers. You could almost fit a hair into it. It's very, 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 very narrow. The inside of that tube is coated with a specific kind of chemical. That chemical will interact with whatever you put into that tube. We take that whole mess and we pass helium through it, or hydrogen through it, or nitrogen through it, primarily helium because it's pretty cheap, or it used to be. And we put that whole system inside of an oven where we can control the temperature very precisely. We take that sample that we've taken out of the environment and we use a syringe and we drive it into the end of the tube and we heat that thing at a rate. And what you have at that point is a horse race. If you imagine I-5 and you take all the different types of horses that exist and you have thousands of each breed and you start them all on the same line and you say go, the fast ones go through first and they cross the finish line first. Slow ones come at the end and I'm the one following up at the very back. It's happening the same way inside of this column, but what's happening in doing the separation in that case is actually boiling point primarily. So things that boil very quickly, they move through very quickly. Things that boil very slowly, they move through very slowly. Once we've separated them out using that method, we put them into the detector, the mass spectrometer part of it. What we're doing there is, as they exit out the end of that tube, we have a little surprise for them. We bombard them with electrons at 70 electron volts, which is actually pretty energetic. Not much can withstand that. Breaks them into pieces. The good news is they break into pieces that are fairly predictable and usually the same. The way I like to describe that is, if we take all the people in this room and we suspend them inside of this great big room and we fire a cannonball at them, the chances are good that each person will produce 2 arms, 1 head, and 2 legs, and a torso. It's very similar when you do the same thing with the molecules. We count those things up. What was that?
I feel sorry for them now.
Well, a lot of them escape, but that's okay. So, yeah, we bash them apart, and then we look at the pieces, and those pieces tell us very specifically what compound got broken apart. Once those pieces get broken up here, that's what this is supposed to represent. We pass them through some magnets, we use some radio frequency, we do some hand waving, and at the other end of it, we have what amounts to an electron capture device, very similar to what's in your phones when you take pictures. As those little charged particles impinge on that detector, it draws a picture. What does the picture look like? That's the picture. That's a pretty neat picture. It turns out that is a picture of Alaska North Slope crude. And if you look down here, for those of you with bad eyes, right down here at this point, it says 5. That is 5 minutes. This scale across the bottom here is time, and this scale going up the y-axis is abundance. So if this is 5, 10, 15, 20, 0 was over here somewhere, this is where that sample got injected into that tube. And these compounds move down that tube. The very quick ones come out first. And as they come out, the computer draws a picture. So each one of these spikes you see here, including all this little hair that's kind of difficult to discern on this picture, each one of those is a specific individual compound. And that pattern that you see is specific and individual for that one geographic area where that oil came out of the ground, where it went through its containment process, where it moved, where it got dumped, and where it got weathered. That's what it looks like. Back in the day, this was about the best they could do. They were using not a GCMS, but a GCFID, which is a flame ionization detector, and this is the picture they could get. You can do really good work with this. You can match things using that. You can zoom. The software allows you to zoom in and zoom out. You could blow this section up to the whole side. And you could overlay one picture with another and try and determine if it's the same. The mass spec allows you a little more detail. So you get the picture, but then how do you do the job? What's the next step? Well, you have to look for specific compounds inside of that jumbled up mess, those tens of thousands of compounds, and you have to start picking out which ones you want to look at. I like to think of it as sand. Right now there's an almost infinite amount of information impinging on you, and you have to navigate through your life. So you get a handful of sand that's all this information approaching you. but you can only process so much of it. You pick out a few grains. Well, we have to do the same thing when we do oil analysis. There's all kinds of information coming at you, but which grains of sand do you want to look at to try and differentiate between sources? You focus on compounds that maintain their concentration between different sources and in weathering. You focus on compounds that have a different variability. Over there in Saudi Arabia, we get a whole bunch of the light-end stuff. Over here on the California coast, we get a whole bunch of the back-end stuff. So you want to focus on those things that are different between different sources. You also want to focus on things that are resistant to weathering. Our friend the hopane you saw earlier, really resistant. Really, really resistant. As a matter of fact, if you went and turned over a rock right now where the Valdez went and had its problem and took a sample and put it through the process, you would find that it didn't look any different today than it did back then. They don't weather. The other thing you look at as you start looking at these things, here's our good friend Alaska North Slope crude. This is the picture I showed you the first time, scaled a little bit differently. Well, when they run through a facility like this, they have to refine it. They're taking cuts out of it. They're trying to make money with it. So one of the cuts they take out of it is this front end cut, the gas cut. There are other cuts out even further, jet fuel, butane. But they're taking a very narrow cut out of it. If you get a sample that looks like this, and the warden brings you a sample that looks like this, well, you're pretty much done in terms of fingerprinting. It's probably not the same. Weathering can't account for that difference. Remember gasoline was over here? Here's kerosene now. A little more, larger section, larger cut of that product came out. Here's diesel, even more. Let's get down to the nut of it now. How can I tell if one sample is the same as the other? Well, at our lab, and in many labs doing this type of work right now, they will take out a suite of compounds, maybe 50, maybe 100, maybe 200. We use somewhere in the neighborhood of 100. And they pick out that particular 50 or 60 or 100 compounds out of that complex mixture, and they make a picture out of it. Here's one such picture. This happens to be the picture that hopanes make out of crude oil. So these things here are well understood. In the literature, you can identify each one of those peaks. I've got a slide later that'll do just that. So you have the mass spectrometer go ahead and make that picture for you on the source sample, and then you have it make the same picture for you on the spill sample. And you do that for each one of those compounds. So you're looking at a great deal of data when you're doing that. And you're using primarily what we're all hardwired to do. Human beings have phenomenal pattern recognition, and you see it in facial recognition. You can do it instantly. You don't even know you're doing it. You see somebody that you haven't seen for a while, you go, I think I know that guy. Well, that's hardwired in you. If you have a lesion in that part of your brain, it goes away, believe it or not. When you look at this, after you've sort of trained yourself to see the things that are there and understand how those peaks got to be there from those depositional environments, explain why the differences that are there might or might not matter, you can read this pretty accurately. As I'm looking at this, I'm looking at the relationship between this peak and this one, and I'm comparing it to this peak and that one. This peak and this one, this peak and that one. These two peaks, those two peaks. And you're doing that pattern recognition across 50, 60, 70, 80 different compounds between a spill sample and a source sample. Here's an example of something that doesn't match. By the way, that's a match. Just so you know. The software will also allow you to overlay this directly, and then you can see differences very, very easily. Sure.
Is there any recognized computer programs that will just search all the databases and say this is a 70% match, this is a 60% match, and you use your judgment to decide if it's real or not?
Yes and no. The problem is once that product comes up out of the ground and moves around or is exposed to the weather and has mixed, those programs, the algorithms those programs use kind of start to fall apart. There are some that will do that screening job for you, just the same way that there's facial recognition software out now. It's almost frightening what it can do for you. So yes, you can screen with it, but it's not very good at coming up with a a legally defensible opinion. As soon as they start putting statistics onto this kind of thing, I'm the defense lawyer. So 98% certainty. 2% are wrong. My client, ladies and gentlemen of the jury, it's not my client's oil, right? So we have to be careful with using algorithms that way. Here's one that's not a match. Our same Hopanes, our friends the Hopanes, I'm picking on them today. If you look at the relationships between, say, this and this and this, these two, here's a big peak that is in one that is not in the other. SJV, San Joaquin Valley Crude, that's drilled just down south of here. And ANS is Alaska North Slope. You can see just in two different areas, those ratios are just different.